Hello and welcome to this lecture on chemical process modeling and simulation. This is the third of three lectures on introduction to molecular momentum transport and viscosity. This lecture is probably one of the most mathematically intensive lectures that we are going to have in this course, and particularly because it introduces some of the mathematical complexities that we will face in this course. And therefore, before starting this lecture, I would like to give this note of request that you please try and follow things along carefully. And of course, as I've always mentioned, if there are any questions, please feel free to post them either in the comment section or contact me. I'll be very happy to clarify. Now, so far, what have we done in the past two lectures on molecular momentum transport? We talked about how, using two examples, molecular momentum transport occurs in fluid flow. Particularly, we restricted ourselves to laminar flow. Laminar flow, of course, is flow of fluids with uniform velocities in each, so to speak, layer or layers or laminae of fluids. The fluid particles, once again, keep in mind that these fluid particles are not fluid molecules. Continuum hypothesis holds. Knudsen number is required to be at least less than 100th, less than 0.01. That means the mean free path for a molecule should at least be 100 times smaller than the characteristic length scale of the system. And therefore, when you are talking about a fluid particle being a system, and the characteristic dimension of a fluid particle is large enough that we can apply continuum hypothesis to that fluid particle and model that particle's flow within the picture of a continuum picture. That basically means that the fluid particle itself is large enough to be of the size of typically of the order of microns. And having presented all of these, now so we looked at laminar flow. In this laminar flow, we observed some key characteristics of this molecular momentum transport. Molecular momentum transport or friction or shear or drag, all of these are similar terminologies. They just, you probably have heard the same thing in so many different names before. Now, all of these basically arise when there is some sort of a contact between a fluid particle which is moving at a certain momentum and either a fluid particle or some sort of a solid surface that is moving at a different momentum, or if it is stationary, for example. And this sort of a momentum gradient results in the transport of momentum from a high momentum region to a low momentum region. This is one characteristic feature that we observed. Now, what is the other thing that we observed in both the examples that we looked at? The fluid itself was flowing in one direction. In other words, the fluid particle was moving in both cases. One is flow between two parallel plates, the other is same two parallel plates but the bottom plate set in motion, called co-ed flow. In both these cases, the fluid particle was moving in the x direction. However, the stationary surface that caused this friction was at a distance in the y direction away from the fluid particle. Therefore, this resulted in the molecular momentum transport of x momentum now being transported in y direction. In other words, there is this momentum. That momentum is carrying the fluid in along the x direction, but that momentum is reduced in magnitude. In turn, it is transmitted along the y direction to another fluid particle and another fluid particle and another fluid particle, each at different y values, until it reaches a surface which is stationary, and that surface absorbs that momentum. The rate at which that momentum is transferred to that surface is definitely not large enough to actually displace the surface. So it simply absorbs the momentum and dissipates it. while remaining stationary. So this sort of established a velocity profile, that it established a velocity gradient, a spatial variation of velocity along the direction in which molecular momentum transport occurred. Right? So in both cases we saw Vx being a function of y. In these particular simplified simple scenarios, we saw Vx being a function of y. This basically was the result of a frictional force or a drag force, or this contact molecular momentum transport, that the rate of transport is the force. The rate of transport of momentum is force, right? This force is denoted by two directions, a pair of directions. One direction is the direction in which the fluid is flowing. The other direction is the direction in which this momentum transport is happening. And we found that these two were perpendicular. So we wrote Fxy. And the flux of that momentum transport, molecular momentum transport, which is rate per unit area. Quantity per time is rate, quantity per time per area, which is rate per area, that is flux. So the force per unit area is stress, which is shear, which is simply, the shear stress is simply the flux of molecular momentum transport, and that was given by tau xy. So this is what we found. Okay, so now keeping this in mind, if I were to generalize this picture to 3D, how will this be? In molecular momentum transport, this picture on the left side, what you see is for fluid flow. This is taken exactly from the previous lecture on fluid flow as an example. The picture is from Bird-Stewart-Light flux transport phenomena, chapter 1. In molecular momentum transport, the convective momentum. Where did this x momentum come from? If you ask yourself, where did the x momentum for the fluid particle come from? It came from either an applied pressure. In the case of the first example, flow between two parallel plates, before the fluid entered the region between the two parallel plates, it had been a pressure had been applied, and that had driven this flow into the region between the two parallel plates. Or in the case of fluid flow, as you can see in this picture, that the lower plate is set in motion, and that displacement of the surface provides the convective momentum. So this is the, so to speak, source of the convective momentum. And what do I mean by convective momentum? It is basically the momentum that the fluid has, which basically allows the fluid to, which basically transports the entire fluid in a certain direction, in this particular case along the x direction. So now the convective momentum in one direction, which is the x direction, is transported along the tangential y direction, either towards the surface or away from the surface, as so-called molecular momentum. Basically the molecular mechanism of transport by way of contact, by way of the sliding motion between two fluid particles, which basically, if you were to look at what happens at the molecular level, it is breaking and reforming of the secondary bonds, right? And the flux of this molecular momentum transport is the shear or viscous stress, and that stress is given by tau xy is equal to minus mu into dvx by dy. There is a measurable, discernible velocity gradient, x velocity gradient in the y direction. Again, you see two directions involved. X velocity changing in the y direction, right? And that velocity gradient is the measure of the flux of this momentum transport. If there were no molecular momentum transport, if basically in the case of the flow between two parallel plates, the entire fluid would have continued to move at the same velocity. In the case of fluid flow, the bottom surface would have moved at whatever velocity it was set in motion, and there would be no frictional force between the the bottom surface and the entire fluid that is at rest, and so the fluid would have continued to stay at rest. The surface would have just kept sliding by with no friction. This is the kind of friction-free problems, motion problems of rigid bodies that you studied. You looked at projectile motion, you assume that the stone that is thrown has it experiences no friction by the air that is present. Or even in earlier classes when you first learned your Newton's second law and used the Newton's second law to solve for rigid body motion in friction-free systems, you learned about, say, a vehicle is moving at a certain velocity, no friction. All right, so basically if it is set in motion, a force is initially applied, it will keep on going. There is nothing to retard that motion, right? But the very fact that there exists this velocity gradient, in other words, the momentum is transported from the surface through the fluid to the top, right? The velocity gradient that exists is a direct indicator that there is molecular momentum transport in the perpendicular direction, right? In the y direction, right? So naturally, therefore, the the magnitude of this velocity gradient should in turn indicate what should be the magnitude of the molecular momentum flux in the y direction. These two quantities have to be related, and the relationship that is given is Newton's law of viscosity. The proportionality constant is the negative sign of viscosity, because the nature of this molecular momentum transport is to retard the motion of the fluid. Now, if we were to generalize this frictional force in 3D flow, in general 3D flow, for the time being in this entire lecture, we will stick to the Cartesian coordinates of x, y, z. There are 6 possible such stresses: tau xy, tau xz, tau yx, tau yz, tau zx, and tau zy. There are 6 such possibilities. Now, there is also the friction of a fluid particle moving in the x direction by another particle in the same layer. Simple example I will tell you. Imagine that there is a long queue. If the queue of people who are standing in one long line, right, they are all very orderly in their movement, then there will be movement without touching each other. But if the crowd becomes so much and the space available is too small, then one starts pushing, one starts pulling. There is this tug of push-pull, right? And that is exactly what I am talking about. This will cause, if this is significant in the queue, what will happen? The queue will break up, right? People will get scattered. Often one line will become more than one line, right? And people who were in the back will try to push and go to the front. People who were in the front will be pushed back. So this is essentially a way for mixing, right? So now I am trying to introduce something that was not so far considered by us in our laminar flow. These fluid particles are all orderly, nice manner. They are flowing in one direction, right? One right after the other, so to speak. Now, when there is this friction, possibility of friction between two fluid particles in the same layer, so one will try to pull the other particle or one will try to push the other particle. In either case, once again, there will be sliding because the cohesive forces are not strong enough. Therefore, these fluid particles may swap positions. In other words, there could be some form of mixing. This results in what kind of a stress? This is also a perpendicular stress because this is along the direction of flow. In other words, there is a tau x in x direction itself. Similarly, there is tau y and there is tau z. Now, I have written that there is another normal stress. What other normal stress exists? The one normal stress that exists is the isotropic pressure forces. The pressure that is applied is a normal stress, isn't it? It is the push, so to speak. There is a line of people that are standing. The last fellow is pushed, and that fellow in turn pushes everybody, and everybody starts moving, right? So it is like that. That pressure force from one end of higher pressure to another end of lower pressure, there is this push, and that is a normal force. In addition to that, there could also be this kind of friction which can cause mixing, which occurs in turbulence, right? So therefore, in all, there are 9 such quantities, 9 such tau terms: tau xx, tau yy, tau zz, and then the xy, yz, zx, and their complementary yx, yz, and zx, xz, components. Now, in addition to this, there is of course the pressure along the x direction, pressure along the y direction, pressure along the z direction. So all together, now, to account for the entire contact or molecular stress that a fluid particle experiences, you need 9 quantities. And all these quantities are defined by a pair of directions. This quantity, such a quantity, is called the entity that has 9 components, each defined by a pair of directions. This is called a second order tensor. Now, this is represented, this can be one of the ways to represent this tensor is by a 3 by 3 matrix. Now, this sort of makes sense because, this sort of naturally builds on what you have learned in terms of vectors and scalars. So you can think of a vector as a first order tensor, which is represented in matrix form as a 3 by 1, 3 cross 1 matrix. Now look at a vector, for example, pxi plus pyj plus pzk. You can write px, py, and pz as a column matrix, right? And then you can then represent a second order tensor as a 3 by 1 matrix of vectors. So each having 3 columns, 3 entries, right? So for example, you have a shear stress tensor or a viscous stress tensor, and I've thrown one more name here called the deviatoric stress tensor. Now, why this is called a deviatoric stress tensor is something that I will probably address much later in a completely different lecture altogether. But just know that that is also a term by which this quantity is known. So you may encounter something like that in books. Now let's come back to what we are talking about in terms of second order tensors. So the shear stress tensor is now comprised of 3 quantities, just as pressure is a vector is comprised of 3 quantities, each of which in case of a vector, the 3 quantities are scalars. Whereas here in a second order tensor, each of the 3 quantities are vectors themselves. And therefore, you have a tau x vector, which is basically the shear stress along x direction, which has 3 components in it: tau xx, tau xy, tau xz. Tau y, which is the shear stress along the y direction, which is 3 components in it: tau yx, tau yy, tau yz. And tau z of shear vector, which is the shear stress along the z direction, which has 3 components: tau zx, tau zy, tau zz. Now, these 3 then can be written as tau xi plus tau yj plus tau zk. Now, before going any further, I want to go back to those 2 examples that we looked at. Now, what did we see in those examples? The flow direction was along the x direction, and the direction of molecular momentum transport was y, isn't it? So that, since we are looking at this shear stress tensor as a flux of molecular momentum, all right, in those 2 examples, flow between parallel plates as well as wet flow where the bottom plate or bottom surface is set in motion at a constant velocity. In both those examples, since the molecular momentum transport occurred in the y direction, whatever be the component of the shear stress tensor that you encounter in those examples should be a component of tau y, because tau y is the shear stress along the y direction, which is the molecular momentum transport flux in the y direction Sure enough, yes, the term that we saw for shear stress there was tau yx. So sure enough, the molecular momentum transport happens in the y direction, but where did the fluid flow? The fluid flowed along the x direction. So therefore, we had this particular term tau yx showing up for shear stress. So similarly, if you could look at it, for example, if you had fluid flow along the y direction and then molecular momentum transport along the z direction, then the corresponding shear stress component would be tau zy, and that of course would be a component in the vector tau z, that is basically molecular momentum flux along the z direction alone. So this molecular momentum flux along the z direction could have been picked up from fluid flowing along the x direction, which would be tau zx, or fluid flowing along the y direction, which would be tau zy, or fluid flowing along the z direction itself in case of mixing turbulence and all that, which would be tau zz. So therefore, you see how this 3 by 3 matrix representation gives rise to a quantity, a 3 by 1 quantity, where each entry is a vector in itself, and together this whole quantity is a second order tensor. Now, if you were to therefore express all these three terms, so I have just written it out at the bottom. Tau x is simply tau xxi plus tau xyj plus tau xzk, and so on and so forth for tau y and tau z. Now, look at how have I written the second order tensor tau? It is tau xi plus tau yj plus tau zk. That means if I were to plug in this expression for tau x that is at the bottom into this particular expression at the top, then my shear stress tensor should be a sum of 9 components. Okay, so in tau x is tau xxi plus tau xyj plus tau xzk. So for all of those, you will have another I, unit vector I, that is showing up. Remember, I told you that these tensors are quantities where you have a pair of directions associated with each term, each term of the tensor, right? So with tau xx, there are two pair of directions, I and I. Tau xy, j and I. J from the tau xyj, and then I because it is tau xi, and then tau xz ki. So like that, you write these 9 components. Okay, so I hope you understand the relationship between the second order tensors and the first order tensors, which are vectors. So then what are scalars? Scalars are simply zeroth order tensors, which is represented by a 1 by 1 matrix, which is basically a single entity. So if you look at it, a second order tensor has 3 entries, each of which is a vector. If you represent a second order tensor by a 3 by 1 matrix, each of the entry would be a vector. Similarly, a first order tensor can be represented by a 3 by 1 matrix in which each element px, py and pz, they are scalars or zeroth order tensors, right? So you have this building up: zeroth order tensors, first order tensors, second order tensors, and you could go on to build higher order tensors as well. There are certain occasions where in nature we see quantities that are described by are represented by fourth order tensors as well. Of course, we are not going to see them in this course in detail, right, in any form of detail, right? So however, you can see this building up that is possible, right? So scalars are zeroth order tensors represented by a 1 cross 1 matrix, which is a single element or single number, for example. So the example for scalars would of course be some properties like viscosity and density. So keep in mind that both the pressure forces and the shear forces are contact forces. These both measure rates at which momentum is transported by virtue of a contact, right? In shear force, it is contact, but it is in a tangential direction, and therefore there are two directions involved. In pressure, it is in the normal direction, and therefore there is only one direction involved. So a pressure force Px can be thought of acting along II, which is basically along the x direction. Pressure force Py can be thought of acting as to be acting along Jj, and pressure force Pz can be thought of to be acting along Kk, right? So taken together, if one were to add these pressure terms along with the shear stress terms as well, so you would get a total stress that comes from contact, right? That comes from contact, and that contact between what? Contact between molecules or contact between fluid particles. And therefore this total contact stress is often also called molecular stress. And keep in mind, in all of these things, if we are considering any general velocity profile, v is equal to vxi plus vyj plus vzk, where vx, vy and vz are scalar quantities, scalar valued functions, which could be functions of x, y, z, and possibly time if the flow is unsteady. So if I were to write this total molecular stress or contact stress, that terminology, that the symbol that is used to represent this molecular stress is pi. And notice that there is a double arrow that I've put on top. That is one way in which you can indicate that this is a tensor as opposed to a vector which would have a single arrow, right? So how does this molecular stress differ from the shear stress? The only difference is that in the three normal terms, normal components, basically the xx, yy and zz components, in addition to the tau xx, tau yy and tau zz contributions from the shear, there is also px, py and pz contributed from the contact pressure terms, right? So therefore the rest of the terms are the same. The rest of the terms are bit of the molecular stress and the shear stress. The off diagonal elements are the same, if you look at the 3 by 3 matrix. And this is basically the pi 3 by 3 matrix that is shown in the center of the slide is a matrix representation of the molecular stress tensor or molecular momentum flux tensor, right? And this, by the way, if you look at it, the picture that is shown here, it captures exclusively the normal modes, the stresses along, or the fluxes along, momentum flux along the normal modes, normal directions by way of contact. Now this is shown in this picture and the table below, taken from the classic textbook on transport phenomena by Bird, Stewart and Lightfoot. Now keep in mind that this molecular momentum transport flux, why we are talking about this is molecular momentum transport flux. It is momentum transport due to intermolecular interactions via contact. Now the molecular momentum transport flux again involves two directions. One direction being the direction of bulk flow and the other direction being the direction of molecular momentum transport. Now finally, the last thing I want to point out in this slide is, if you look at the table, the second column, vector force per unit area on the shaded face. Of course, if you go to the book, each of this term is shown in greater detail in pictures like this. A certain face is shaded to sort of point out what was going in the II, JJ, KK. They are all shaded to show basically how these terms come about. I urge you to look at it for more clarity. Look at the textbook on transport phenomena by Bird, Stewart, Lightfoot. This is in the first chapter, very first chapter, for more clarity. Now, what I would like to point out in this column is this basic, the three terms that you see here with a delta with subscripts. This is basically nothing but the Kronecker delta, which basically is, it either assumes a value of 1 when I is equal to j, the subscripts are equal, or it assumes a value of 0 when the subscripts are not equal. Now, if you were to look at these three columns, the x component, y component, z component, each having 3 entries, if you were to look at these together as a matrix, a 3 by 3 matrix, you will notice that for the xx component, yy component, and the zz component alone, you see the pressure being written, and when I not equal to j, the Kronecker delta values is 0, and therefore for tau xy you don't see a p term added, or similarly for tau xz you don't see a p term added, right? So this pi x is again something similar to the tau x vector that I had shown, to show how a 3 by 3 matrix can be, a second order tensor can be written as a 3 by 1 matrix, a column matrix, where each entry itself is a vector, right? This pi x, pi y, and pi z are such vectors. Together, taken together, they will form a tensor, which is the pi tensor, and the 9 terms are shown on the right hand side with this 3 by 3 matrix given by the 3 columns: x component, y component, and z component. Now, so we move on now to the next part of this. So now we have defined the fluxes of molecular momentum transport, and in defining these fluxes we had to introduce the concept of second order tensor, because now we are looking at a quantity that is transported, which is momentum, which itself is a vector, and therefore we have to look at change in the direction of that momentum, and from one direction to another, and therefore there is a second direction which will lead to another vectorial quantity, and therefore together we got a second order tensor quantities, right? Now the next part of this lecture, the other half of this lecture, so to speak, has to do with relating this molecular momentum transport fluxes and rates to the fluid properties, to what is happening in the fluid. How does the fluid respond? There has to be some sort of a model for this, right? A fluid model for this, which of course is, as we saw in the two example lectures that we, previous lectures that we saw on introduction to molecular momentum transport, the constitutive model that captures the dependence of this molecular momentum transport flux on the fluid properties is the Newton's law of viscosity. So we are left with the remaining part of the lecture to generalize Newton's law of viscosity into 3 dimensions. And so not only are we looking at the viscosity, particularly the property of the fluid itself, but we are also looking at the driving force for this molecular momentum flux. Why is there a shear stress that is coming up? Why is there this momentum being transferred from one layer of a fluid to another layer of fluid? What did we conclude? We concluded that molecular momentum transport occurs from a region of higher momentum to a region of lower momentum. In other words, there has to be a momentum gradient. You know, in this development of this Newton's law of viscosity, instead of momentum gradient being taken, it is the velocity gradient that is being taken, the mass of the fluid not being captured, which is of course why your viscosity has, in its unit, it has kg as well, kg per meter second. Kg is there as well because the right hand side, the driving force does not capture by itself, just that term itself does not capture the mass of the fluid particle, the two fluid particles across which this molecular momentum transport occurs. But anyways, looking at the driving force from the region of higher momentum to the region of lower momentum, this molecular momentum transport happens, and therefore the driving force is the velocity gradient, right? And that velocity gradient has to be captured as well. Now, how do we go about generalizing this Newton's law of viscosity into 3 dimensions? Now, before we proceed any further, I want to point out two things about the first equation that is written here. Now, I have written a general expression where I have said tau with a subscript of ij is equal to minus mu into dvi by dxj. Now, you notice that till now we were talking about x, y, z. Suddenly I have abandoned this x, y, z. Now I am writing this in sort of a general coordinate system. Now come back to the bottom right box that is here on this slide. You would see that the value of I, of course, it's also true for j, I and j, the values could be 1, 2 or 3. In Cartesian coordinate, this could be x, y, z. In cylindrical coordinates, this would be r, theta, z. In spherical coordinates, this would be r, theta, phi. And if you looked at any other general orthogonal coordinates, it would be 3 terms, whatever you define them to be, those the variables representing, independent variables representing those coordinates, right? So what is this tau ij? So this tau ij could be, for example, tau xx, tau xy, tau xz, tau yx, tau yy, tau yz, tau zx, tau zy, tau zz. I am, stating out all the 9 components. I'm only going to do this once. I've only done it once. I'm not going to do it again. But the point is that this representation tau ij is the representation of the tensor itself. And so this gives rise to a fairly convenient notation of representing a second order tensor. A matrix could be represented like this, right? Instead of writing out the 9 components, and even more painfully, instead of writing out tau xx I plus tau xy ji plus tau xz ki plus, and so on and so forth, writing out all of that, right? In a simple fashion, it is possible to represent that second order tensor as tau with a subscript ij. This, you would see, is the most commonly used notation for representing tensors in advanced books in fluid dynamics as well as in transport phenomena, right? You would see this thing as mentioned as Einstein's convention, right? So this is sort of to introduce you to that convention as well. We are not going to stick past this this lecture. We are not going to be seeing this sort of Einstein convention, or even for that matter much of the tensor algebra or calculus, except when we derive the conservation equations. After that, we will take the conservation equations to be granted, and then once we have derived them, we have all the liberty to do that because we have derived them, right? So we will take them for granted and then start applying them to different situations where we will always be looking at a 3-dimensional system, which will simplify mostly either to a 1-dimensional or a 2-dimensional system, and therefore we will not even be looking at much of this kind of a mathematics. But still, I want you to become aware of these kind of notations. In case you go ahead and study more advanced courses, you should be familiar with this kind of notations. So this is like a small, in a very simple expression, 2 tensors are expressed as if this is like a relationship between 2 scalar quantities, right? Similarly, dv by dx is also dvi by dxj is also a tensor, right? So depending on what is 1, what is 2, what is 3, you can have 9 components, right? So there is a velocity gradient tensor on the right hand side and shear stress tensor, or as I want to keep hammering it, it's probably not stated enough in most books. It is shear stress tensor, or aka also known as molecular momentum flux tensor, if not accounting for the pressure, right? So such a velocity gradient, now that we are looking at the velocity gradient, this velocity gradient can be thought of to be made of two parts. What have I done here? I have done a little bit of a mathematical jugglery, right? What have I done? I have taken dou vi by dou vi dou xj, and I have split it into two parts. Half dou vi dou xj here, and then another half dou vi dou xj in the other brackets. And then I have taken the transpose of this. Basically, instead of dou vi dou xj, I have dou vj dou xi. I have added to one tensor, I have subtracted it in another tensor. So if you keep in mind that all of these are tensors, they look like they are all simple scalar quantities. Really speaking, what the left hand side is a 3 by 3 matrix, and then that 3 by 3 matrix is considered is written now as half of that matrix plus another half of that matrix, and then what has been added is to this 3 by 3 matrix, one 3 by 3 matrix is added, and that exact 3 by 3 matrix is subtracted from the other half. So essentially the two terms will, dou vj dou xi, will cancel themselves out, and then we will be left with the velocity gradient again. So the first part, all right, the first part, which is half of dou vi dou xj plus dou vj dou xi, is called the rate of strain tensor. This captures how much strain a fluid experiences. All right. So why this is the case, I am not going to explain in great detail. I would leave you to refer you to advanced textbooks in fluid dynamics to go and refer to. Now, notice I have put this in blue, arrow as well as a cloud, that these are all tensor components. These are all not scalars, just so you keep in mind, right? So this is called the rate of strain tensor. The second term is called the vorticity tensor. What is the vorticity tensor? Now this I will just indicate to you a little bit, because pretty much this is about all that we are going to look at vorticity in this course. You should really be looking at an advanced fluid dynamics course, or a course in transport phenomena, where these quantities can be discussed in greater detail. To introduce you to modeling is, I should not lose sight of the fact that this is a modeling course, right? Modeling and simulation course. So this discussion is at a very preliminary, very introductory level, and of course this is aimed at undergraduate students as well. So keeping all of those in mind, this discussion is at a very preliminary level. Now, what have I written here is that this vorticity tensor I have written is half of del cross V. What is a cross product? What is this cross product called? This cross product is called curl of the velocity. Now del cross V, what is del? Del is an operator, of course. Dou xi plus dou yj plus dou zk. It's a vector operator, and which is why, of course, I'm able to take a cross product of it with another vector, which is the velocity, right? If one were to take that cross product and look at basically what the terms are involved in, what the resultant terms are, each of the term will look very much like this. Okay, so that is something that I will leave you to work out as a simple back of the envelope exercise to check this is the case. And what you have learned in your calculus that the curl of a vector, it indicates rigid rotation. All right. So this is rotation of the fluid as if it is a rigid body, and that will not cause any shear, that will not cause any friction, and therefore this term is not going to contribute to the strain, to the shear stress. Therefore, the shear stress is going to come from the strain, rate of strain tensor, which arises from deformation of the fluid layers under contact stress. And this is exactly what we are talking about. This was what we were talking about when we were talking about sliding. When I appealed in a very qualitative manner to your prior understanding of breaking and reforming of secondary bonds between fluid particles, or at least between molecules that form the edges or the interfaces of the two fluid particles that are coming into contact, a few layers of them at least, of these molecules, right? Now this breaking and reforming of the secondary bonds, which causes this sliding motion, which causes this friction, which causes this slip, so to speak. That means that the fluid particle is being deformed. So one molecule, by virtue of interaction with another molecule, one molecule in one fluid particle, by virtue of its interaction with another molecule in another fluid particle, literally tries to drag this molecule along, and that is what causes that entire fluid particle to, so to speak, deform. And this deformation is what is captured in the rate of strain tensor. And as I said, I am not going to go into any further details on this rate of strain tensor. You are more than welcome to go and look at how these deformations are defined, and this would be indeed the case. In fact, the rate of strain could be defined for even solids, right? So elastic bodies could be described by such rates of strains as well, under the influence of some sort of an applied force. And you can see similar, unsurprisingly, right, similar such expressions coming for deformation of solid bodies, elastic bodies as well. Of course, there is no such thing as viscosity there. You will see other proportionalities of constant, and I do not want to get into further discussions on this. Right. The other thing I want to point out, this is something that is stressed repeatedly in advanced transport phenomena and advanced fluid mechanics courses, is that the shear stress tensor is symmetric, and this means it is invariant to transpose. Okay, in other words, we had these two terms. I made a big fuss about tau xy, tau yx, tau xz, tau zx, tau yz, tau zy. If a tensor is, if a 3x3 matrix is symmetric, this means its transpose is the same as that matrix itself. That means there is no variation because I have taken a transpose. All right. That means what does it imply? Tau xy is the same as tau yx. In other words, if the fluid is flowing in x direction, and by virtue of friction, momentum is transported by this friction, molecular momentum transport, to the y direction. So that would be, so fluid flowing in x direction, molecular momentum transport in the y direction, right? This would be captured as tau yx. And the opposite scenario, where the fluid were flowing in y direction, and by friction, molecular momentum transport causing the momentum to be transported in the x direction, that would be captured by tau xy. These two are equal. It doesn't matter which direction is the direction of flow and which direction is the direction of tangential direction of molecular momentum transport, right? The stresses would be the same, and the rates of strain also should be the same. The shear stress tensor is symmetric and the rate of strain tensor is also symmetric. Whereas vorticity tensor is anti-symmetric. What does this mean? There will be a negative sign that will show. I'm not going to discuss this further. Proofs can be found in many advanced fluid mechanics texts, and that is another mathematical way of saying that vorticity won't cause shear, right? So with this picture of velocity gradient, rate of strain, and vorticity, now we have looked at what happens to the fluid. What are the motions that are possible, right, when you are subjecting a fluid to some sort of a contact stress? So that could be either a deformation or there could be a rigid rotation. The translational degree of freedom and the rotational degree of freedom are both addressed by this particular molecular momentum transport, right? Now, so that side is there, and then of course the one other side, the left hand side in the Newton's law of viscosity, is basically the flux itself. The flux is caused by this driving force of velocity gradient, which comes from strain or deformation of the fluid particle arising from friction. So far so good. With this idea, we can ask this question finally: what is the relationship between the molecular stress tensor and fluid properties? To answer this question, of course, to arrive at the generalized Newton's law of viscosity, okay, so I have done a bit of circular logic here. I have taken, used your understanding of Newton's law of viscosity to sort of set up the terms on the left hand side and right hand side, and I'm going to show back to you the generalized version of Newton's law of viscosity. But you know, we are not in the business of rigorously proving any of these in this set of lectures anyways. Now, so what is the relationship between molecular stress tensor and fluid properties? And this relationship should make sense whether the fluid is moving or the fluid is static. Now let us look at the two cases. First, let us look at what is the relationship, how do we obtain a relationship, okay, between molecular stress tensor and fluid properties when the fluid is at rest. If the fluid is at rest, then the velocity is zero, which means there is no velocity gradient, which means there is no driving force for any shear, and therefore all the shear components should vanish. All your tau xx, xy, xz, yx, yy, yz, all of them should vanish, which means the molecular stress tensor is simply that it contains only the diagonal elements px, py, pz, and this pressure is isotropic. And once again, that is something that you would have learned in your fluid mechanics course, that the pressure doesn't have any preference for direction. It's isotropic. It is given by the scalar pressure, and this scalar pressure can be obtained for a static fluid from thermodynamics by, say, some equation of state, okay, P given as a function of rho and T, or volume and T, a volume number and T, and so on and so forth. Now, of course, this would be such equations of state are difficult when you have long range interactions in these fluids, for example with electrolytes, ionic systems, and then there are activity coefficient models that could be used, unifac, all those theories that are there, which is part of thermodynamics. We will not get into much detail in this lecture about this part, though we will address this question at some level of detail in one set of lectures after we discuss all transport related models, right? So for static fluid, the relationship between molecular stress tensor, which is simply it reduces, collapses into a scalar called pressure, and that pressure can be related to the fluid properties by way of some thermodynamic model for that fluid. Typically, as an example, it is an equation of state. Now what about moving fluids? Okay, moving fluids, some assumptions are made. First is that the stress tensor is only a function of the rate of strain tensor and temperature. In other words, we are looking at a local model of the stress-strain relationship. This is exactly what we've been talking about. There are two particles that are fluid particles that are in contact. Okay, they mutually deform each other. Okay, so I am not talking about what is the effect of some fluid particle that is 10,000 particles away from this particle under my consideration. Okay, how does that particle which is 10,000 particles away deforming my particle? I am not looking at any kind of a global relationship. I am strictly looking at local relationships. One. The second assumption that is made is that the stress-strain relationship is same everywhere. There is no preferred direction for this relationship. In other words, there is no preferential xy direction relationship over a yz direction relationship. Though, of course, if there is a pressure or force driving the fluid to be flowing in one direction, obviously tangential to that is where there is going to be basically the shear stress. All right. However, given that there is safe pressures from all three directions, suppose, all right, this flow is in some resultant direction maybe, and there is no preferred direction for this stress-strain relationship because the fluid is isotropic in nature, and that is the assumption that is made. Of course, this will not be true for long chain molecules. Suppose you have polymeric liquids. All right. By definition, your polymers are molecules which are highly anisotropic in nature, right? So you have long chains. So if you look at the dimension of the polymer chain in one direction versus another direction, if I stretch out the chain, in the direction in which this chain is stretched out, the dimension is very, very large. But in its perpendicular direction, it is the molecular diameter, which is probably angstroms. So basically, for long chain molecules, one cannot claim that the stress-strain relationship does not have a preferred direction. So this model is not valid, strictly speaking, for polymeric liquids. Okay, such fluids for which I can assume, one, that the stress-strain relationship is local, and two, that the fluid is isotropic. Such fluids are called Stokesian fluids. Finally, what we assume further is that we assume a linear relationship between shear stress tensor and the rate of strain tensor. Now, there is no reason this relationship has to be linear, and you have studied, have heard of, and encountered in practical life what are called non-Newtonian fluids, for which this relationship need not be linear, right? So, however, in this particular discussion, we are confining ourselves to generalized Newton's law of viscosity. Then, therefore, we are assuming a linear relationship between, on the one hand, shear stress tensor, and on the other hand, the rate of strain tensor. Thus, the generalized Newton's law of viscosity relates two second order tensors, right? One shear stress tensor, one rate of strain tensor. In principle, the general coefficient that relates these any two tensors, should itself be a fourth order tensor. Does this make sense? I am not sure. Okay, so that there could in principle be a fourth order tensor that could relate two tensors. Now let us reduce this. Okay, what we are talking about is you have a 3 by 1 vector, and then that 3 by 1 vector could be obtained by multiplying a 3 by 3 vector with a 3 by 1 vector, right? So you would get a 3 by 1 vector, right? So you can have in principle 9 coefficients, right? In place of a single coefficient. Similarly, if I go one level more, so I could have 3 power 4 or 81 coefficients. I, J, L, M are 4 subscripts. Ij for the shear stress, Lm for the rate of strain. There is no reason why these two should even be correlated at all. All right. So of course that is not the case. What we look at x, y, z in all in all the systems, both the velocity gradient or rate of strain tensor as well as shear stress tensor. We look at x, I, j and lm are is the options are 1, 2, 3 or x, y, z if it is Cartesian coordinate. But there's no need that they need to be, mathematically speaking, then they need not be the same. So in principle, that would be 81 coefficients. However, the isotropic nature of the fluid and the symmetry of the shear stress tensor, I'm not going to once again go into why these two result in the reduction of number of coefficients from 81 to 2. And I'm not also going into the details of why those two coefficients are scalar. But I'm going to leave this final, so to speak, expression for the shear stress tensor as a function of these the velocity gradient terms that are there. All right. Now there are two sets of terms, as you can see. The first term has a coefficient a, which is a scalar. All right. It has what we saw as the velocity gradient, dou vi by dou xj plus dou vj dou xi. The second term has a Kronecker delta, and then what is inside the brackets, okay, that is basically divergence of velocity, del dot v, right? Dou vi by dou xi plus dou vj dou xj plus dou vk dou xk. So the second term captures the divergence of the velocity field, which velocity vector, and the first term captures the velocity gradient. Okay. Now there are two constants, one is a and one is b, and these two are defined in terms of two fluid properties. One property is the shear viscosity mu. The second property is the dilatational or volume viscosity kappa. We will spend just one slide on what this kappa term, when this term will become significant. So the definition for this a and b are given below, where a is shown in the red color box, maroon color box, and b is shown in the blue color box. Now let us look at what are these terms in the vector tensor notation. The top left you see dou vi by dou xj plus dou vj by dou xi. This is Einstein notation. This basically, the dou vi by dou xj is basically a 3 by 3 matrix. This is what I told you, if you recall. It looks like a very deceptive scalar, this Einstein notation. I can change I123, J123, and therefore I will get a 3 by 3 matrix, and this is the matrix. So this can be thought of as three quantities, 3 by 1 matrix, in which each of those quantities is a vector. So that is basically dou v by dou xi I, dou v by dou xj j, and dou v by dou xk k, right? So this is your gradient. Your del operator is dou by dou xi I plus dou by dou xj j plus dou by dou xk k. That is your del operator. That operator is operating on that vector operator is operating on a vector field, and therefore you have a second order tensor, which is the velocity gradient tensor. And what is dou vj by dou xi? Now I am flipping the indices. That's it. So I am essentially taking a transpose of this matrix. All right, and therefore the second part is simply the transport of the velocity, transpose of the velocity gradient tensor. That is simply del v transpose. So the first part of generalized Newton's law of viscosity, which contained this sum of these two tensors at the top left box, the first part of the generalized Newton's law of viscosity is minus mu, which is a, into del v plus del v transpose. This is the first part of generalized Newton's law of viscosity. So all I'm doing is taking that expression in the previous slide for the generalized Newton's law of viscosity, which is written in the Einstein notation, and I'm converting it into vector tensor notation. That's all. The second part captures the captures the divergence of the velocity field. The del dot V is this term, dou Vi, dou Xi, dou Vj, dou Xj, dou Vk, dou Xk. And the direct delta coefficients del Ij, when I equal to j, it is 1, I is not equal to j, it is 0. Remember, this is what we saw in that table from Bird-Stewart Lightfoot also. So this is the unit tensor. So this is 1, 1, 1. Actually, these diagonal elements, del 1, 1 is equal to 1 because I is equal to j. Del 2, 2 is equal to 1, I is equal to j. Del 3, 3 is equal to 1, I is equal to j. This is simply a unit matrix. In a matrix parlance, it's a representation of a unit tensor. All right. Of course, all the other terms when I is not equal to j are 0, right? So this Kronecker delta that is at the top left, okay, the term that is there with the Kronecker delta at the top left can be represented as a unit tensor, and then that multiplies a del dot V, which is a scalar quantity, which is the divergence of the vector field, and then you have the second constant, which is B, which is 2/3 mu minus k. Therefore, in vector tensor notation, the generalized Newton's law of viscosity is tau, which is the shear stress tensor, is minus mu into the sum of velocity gradient tensor and its transpose, plus the second constant 2/3 mu minus kappa, which is the dilatational viscosity, multiplied by the unit tensor multiplied by the divergence of the velocity vector field. So basically, whatever terms are going to come from the second term, they will get added to the diagonal elements because this is the unit tensor. Remember, del is the unit tensor, right? So it will get added to the diagonal elements of this first term. All right. So that is what you have to keep in mind. So bottom in the second equation that is shown, it is exactly the generalized Newton's law of viscosity that was written 2 slides ago in the Einstein notation. So this is the vector tensor notation, that is the Einstein notation. Well, all said and done, all the mathematics is all there, which is all great. What is the important conclusion that we can draw from the generalization of Newton's law of viscosity is that there exist two fluid properties. One is called mu, which is the shear viscosity, and the second is kappa, which is the dilatational viscosity, that relate the shear stress with the velocity or the flow of the fluid. The nature of the fluid flow dictates how the molecular momentum flux is going to be, right? That is captured by two fluid properties. So when is the dilatational viscosity important? A dilatational viscosity of a fluid is relevant only when the divergence of the velocity field of that fluid is non-zero. The del dot V term that is seen here, if when this is non-zero, then this term, the second term, gets added to the first term. Well, for incompressible liquids, incompressible gases as well, incompressible fluids, del dot V is 0 and therefore kappa is not relevant. For ideal monatomic gases, without going into a model of the dilatational viscosity of a fluid, or rather how does the fluid model come up with dilatational viscosity without going into the molecular origins of viscosity, these would be discussed in a transport phenomena course. The kappa is 0 identically for ideal monatomic gases. Dilatational viscosity comes into play when there are problems such as sound absorption in polyatomic gases. For example, I am now speaking and this sound is being recorded by the computer. Now what is happening? The sound waves that are generated are transported through air. And what is this wave propagation like? It is based on, as you have studied in your school, compression and rarefaction of the air, right? So depending on the compression rarefaction, the frequency and the intensity of it, the audio that you are hearing is going to vary. And this compression and rarefaction or expansion of polyatomic gases in sound absorption is a problem where obviously del dot V will not be 0 and therefore dilatational viscosity of air would be important. Similarly, when you have fluid dynamics of liquids containing gas bubbles, when you have gas liquid flows where gas phase is dispersed in liquid, where you are creating gas bubbles. And there are a number of examples that I can think of where these kind of situations arise. They can be used for enhancing heat transfer, mass transfer. They can be used for enhancing gas liquid reaction kinetics, right? So in such problems where you have these gas bubbles, they will be subject to compression and expansion, right? And this would be another situation where the divergence will not be zero, and you will have the fluids, the gases, dilatational viscosity would come into play in determining the kind of shear stress, the molecular momentum transport that takes place in such systems. Um, I I sort of realized that I have not given you an actual molecular model of a fluid. I have not given you a model that describes the molecular origins of viscosity, whether it is shear viscosity or dilatational viscosity. And how does this model reflect or change when the fluid is a gas versus a fluid is even in gases, monatomic versus diatomic or polyatomic, and versus what if the fluid is a liquid, what if we have solids. Of course, this picture of fluid flow is not relevant at all for solids. So at least for gases and liquids, I realized that I have not given this. Now that model is something, if it is of interest, I could after the rest of the course is done, I could record a separate lecture and present that model to you. That would probably help answer a lot of the questions that you may have faced, because of the frustration of taking things to a certain point and then saying that you can refer to other textbooks and not giving the full picture, right? But I had to limit myself, because as you can see, this already is the longest lecture that I recorded, easily more than double the length of many of the lectures that I've put out so far, and I'll be putting out for the rest of the course. And this is already very, very loaded with concepts. And I also had to draw a line in terms of what is within the scope of chemical process modeling and simulation as a course aimed at undergraduate students. Okay, so I hope that rather than feel frustrated by some of the incomplete ideas that have been presented in this course, I hope that that incompleteness instead spurs your curiosity further and propels you into going and referring to other textbooks and reading and expanding your understanding. I'd be, as always, very happy to answer any questions that you may have. Please feel free to leave those questions in either the comment section, or you are welcome to contact me, and I'll clarify the doubts you may have and answer the questions you may have as best as I can. I don't want to drag this lecture any further. Thank you for listening to this. Have a wonderful, wonderful day.